Okay, folks, here we are at chapter 10, which is all about circles. So we're going to talk about everything that we could possibly think about with circles. And so we're just going to do a basic introduction for section 1. And we're going to start off by talking about the definition of concentric circles. So the definition is that you have two or more circles that are all in the same plane, so that's the coplanar part, but they all have to have the same center. So it ends up looking kind of like a bullseye or a target. You can have as many circles as you want, but they're never going to intersect each other, and they all share the same center. Okay, so there's not really much more we can say about that. The next we're going to talk about is congruent circles. So what does it mean for two circles to be congruent? Well, the only way that we would be able to say that they would have the same measure would be if their radii were actually congruent. So if you look at these two circles and we would say that, they both have the same measure for their radii, we would be able to say that the two circles are congruent. Likewise, if you know that the two circles are congruent to each other, then you can say that the two radii are congruent. So that's just your definition of congruent circles. That will come in handy. Okay, moving on. Okay, so this is where the meat of the section is, talking about these radius-chord relationships. So first of all, what we need to understand is what they mean when they talk about the distance from the center that a chord is. So hopefully you guys remember what a chord is. A chord is this segment here that intersects the circle in two places. And they're talking about the distance that this segment right here is away from the center of the circle. So whenever you measure distance, you always want to measure the shortest distance. And that's going to be along the perpendicular line. So what you would do is if you have your chord, you would start from the center and draw a line that's perpendicular to that chord. Okay, so what's interesting here is when we do this, okay, so here's my perpendicular. What can happen is if you were to connect an endpoint of the chord with the center of the circle, you end up getting a right triangle. And with this right triangle, you know that this radius right here, they should tell you what the length of the radius is. You have the hypotenuse. And then we'll be able to look at the length of one of the legs or the other leg and be able to solve for the missing side. Okay, so that's really what's going to be going on in these next two theorems that we're going to talk about. So the first one, Theorem 74, talks about that if you know a radius is perpendicular to a chord, so here's a radius, Fn, if we know that it's perpendicular to this chord, then we know that it also bisects the chord. Okay, so that's going to be really important, and we are going to end up using this theorem in a proof. So if we needed to use this theorem in a proof, this is the reason that we would say it. It says if a radius is perpendicular to a chord, then it bisects the chord. That would be the shorthand. Now, not only are we going to use these in proofs, but we're also going to have a lot of computational questions as well. So for example, if we look at this diagram right here with this circle F, if they tell us that Fn is perpendicular to GL, so I can go ahead and make my little perpendicular symbol here. Okay, if we know that, and then they tell us that GL has a measure of 12, and we know that the radius is 10, they're asking us to find the distance away the chord is from the center. They're saying find Fm. Okay, so first of all, using this theorem that says if we know a radius is perpendicular to a chord, then we know it bisects the chord. And if this chord has a length of 12, then bisecting it means that Gn right here, Gm, sorry, is going to be 6 units. And then the radius, not only is Fn a radius, but when we connect F to G and F to L, those are also radii. And they're radii of the same circle, so that's also going to measure 10. So what we can do is we can place our values of 6 and 10 for these sides of the right triangle. And now it's just using your Pythagorean theorem, or if you're on top of things, you can see the triple to help figure out what Fm is. So using our triple is actually the 6, 8, 10 triangle, we know that Fm measures 8. So these are the kinds of computational questions that you're going to end up doing. So just remember that you're going to look at your chord and your radius. Sometimes the radius doesn't go all the way through to the circle's edge here. It might stop right here at M. But if you know that this is perpendicular to the chord, it still is going to bisect the chord. And then you can use your right triangles. Okay? All right, so let's look at the other theorem that we have for this section, which is Theorem 75. And this is kind of like the converse of Theorem 74. And it says that if a radius bisects a chord, which is not the diameter, right? Because the diameter is a chord. So you know that if a radius bisects the chord, then you know it's perpendicular to the chord. Okay, and if we were going to use that in a proof, we would say if a radius bisects a chord, then it's perpendicular to the chord. Okay, last theorem. This one's not as interesting. It's not something we're going to use that much. Definitely not going to use it in a proof. But it says that the perpendicular bisector of a chord is going to pass through the center of the circle. So pretty much if you had a chord right here, QP, and I did the perpendicular bisector, and I made sure that it passed through the center, that it would bisect it, and it would be perpendicular. So we would know this, and we would know this. So that's all that that theorem is really saying for us. Okay? All right. So next. Proofs. Aren't you excited? We're back to proofs. Okay, here we go. It says we have circle Q, and that QT and RS are perpendicular. So I'm going to go ahead and mark that. Okay. And we are supposed to prove that QT, this ray, or I'm sorry, TQ, that ray right here, bisects angle RTS. Okay, so we have our givens. From our givens, what we're able to say is that angle TPR and angle TPS are going to be right angles. And that's because of our definition of perpendicular, obviously. And then we know that they're going to be congruent because right angles are congruent. Okay, and then the next one, this one is using our new theorem that said that if a chord, or if a radius is perpendicular to a chord, then it bisects the chord. So we can now say that QT bisects RS. And there's our theorem. So I can go ahead and mark that these are congruent. Okay. Next, I'm going to say that PR and PS are congruent by the definition of bisect. All right, I can say that TP is congruent to TP because of the reflexive property. You guys should all be totally fine with this by now. Ooh, that was a really big circle, sorry. And now you should see that the two triangles are congruent by side angle side. For CPCTC, we're going to say the two angles are congruent, and then we can use our definition of bisect to say the angle has been bisected. So really all of this after step 4 is all old news for you guys, right? You guys are pros at that. Okay, so there you have it. That is the first section of chapter 10. All right, see you later.